This video will continue with chapter 10 and we'll actually start solving some full problems. So previous video, we laid out all the steps. Step 1, forming the two hypotheses. What we used to know, how we are challenging that original thought. Step 2, setting up the critical region. Starting off by getting the left tail, right tail, or two tails based off what we did for the alternative hypothesis. And then looking ahead to know what standard deviation, to know if we should use which chart, and to get the critical T or Z, and finish getting that labeled. Step 3, use the actual sample data to get an appropriate test T or Z value, and then compare. Is this Z or T in the shaded region? And to then make the appropriate conclusion. The last thing I will say as we do this problem, the book likes to do this and then talk about getting a p-value, the area in the tail based off of this ZT. So they make their conclusion slightly differently. They point about if the p-value based from this is less than alpha, then your p-value is entirely trapped in here. So that would go along with this situation. But if your p-value is bigger than alpha, then you must be, your test value is outside of this critical region. So again, it sounds similar, but it's just so slightly different, but still doing the same thing. Okay, so now let's start to see a full problem. So I've got this whole situation laid out for us. We've got previous research suggests people who commute to work, it takes an average of 43 minutes. City planners are building a new subway line hoping to reduce this time. After the subway was built, they surveyed 100 commuters, found they had an average commute time of 41.8 minutes with a standard deviation of 3.7 minutes. At a level of significance of 0.01, is this proof the new subway line reduces commute time? So there's a lot here, everybody. That's a very big, full, lengthy problem. As we have suggested multiple times, that's always kind of the situation here. Kind of the situation for the last couple of chapters. But reading through, it's easy to get bogged down, but notice the difference. Our probability problems were long and lengthy, but always kind of finish with, hey, what's the probability? Find the probability of this. What's the probability of that? There's no mention of probability here. Okay, our confidence interval problems look long and lengthy like this. But similarly, you read through, there's a lot of information, and in those problems, you'll notice some similar information that's given in these problems, but it never asks for a confidence interval. So some people can kind of initially start identifying hypothesis testing by default, but if you really were understanding what we were saying in the previous video, it's all about testing a claim. Looking at a situation, looking at what we used to know, and in some way trying to improve on that situation. That's exactly what we have here. We have some previous information about commute time, and we're trying to improve. This whole idea, the new subway line, is aimed at reducing this commute time. So that's where we're going. And this is what we used to know. And with this new technique, with this new subway, we're hoping to reduce this time. So there are the two hypotheses. The null hypothesis, what did we used to know? Well, we take them for what we say. Previous research, this was the average commute time up here. So that my null hypothesis, mu equals 43 minutes. I like to include the units here. But as I always say, even though that's all you write, you should be able to put a sentence together here. And for this one, I will completely write it out here. The average commute time, I mean, you could put in for all people, that's the idea of population, but simple enough, the average commute time is 43 minutes. There's your sentence that goes directly with this little bit of notation. But now the alternative hypothesis. We're doing something new, and how does that new something, how does that change what we used to believe? So notice this important point, everybody. Too many people, when they make their alternative hypothesis, they're too dependent on the other pieces of information. so that they see 43 minutes up here, they see 41.8 minutes here, this is less than this, and that's how they decide mu is less than 43. Now, at least that one happens to be correct, but that's lucky, okay? One other quick thing that's wrong. People think the alternative hypothesis is mu equals the 41.8. Go back to the beginning. We never will make the alternative as another equals. It's always going to be an inequality, a less than, greater than, or not equal to, comparing to the original total. But now, why is the less than correct? It's not because of the new sample data. It's because of what they actually set up here. They're building this new subway line. Now, this may seem obvious. We're not building subway lines to make people take longer to get to work, but it clearly had to be stated. Without saying we are hoping to reduce time, all we can do is just say mu is not equal to. But by saying reduce this time, we want the average time to be less than what it was. That's why we get this. So now we can kind of add the whole idea with the new subway, because that's the new change here. But really, now our alternative hypothesis, how are we challenging? We're saying the commute time is less than 43 minutes. So something changed, and I acknowledge that, but here's the main point. What we used to believe and how that is being challenged. And now that I did a good job in step one, you really can't skip steps here, everybody. You really have to be very methodical here. And that's why I do like to point out the 4-step process. Kind of keeps people a little more on track. What comes next? So I established I was looking at a hypothesis test. I saw information. Even at the end, everybody, I've pointed out previously, you get to the end of a word problem. That's typically where you get your information. What type of a problem? That's typically where we'd see find the probability that something happens, or find the confidence interval. Well, here, the end of the problem is all talking about, is this proof the subway line reduces commute time? There's that word reduce again, one more time reinforcing the less than idea. And one more time, this whole question is a challenging statement, is a new thought, a new hypothesis that challenges an old idea. So even again, reading through, we should see this as a hypothesis test. Now we've got our hypothesis set up. Well, the alternative was a less than, so step 2, I set up my critical region picture. And I know that'll be a left-hand test, right? I'll use the left tail. The less than always goes with the left tail. I need the area that goes with that. A level of significance of 0.01, that was given. That's alpha. So that'll go right here. But now I need to figure out Z or T. I've set up my critical region. The last part of step 2 is to now get the critical Z or T score that separates this region from the rest, the shaded region and the tail from the rest of the non-shaded. Well, I'm on the left side. It's definitely going to be a negative, but Z or T, all about the standard deviation. So I go back to the problem. Well, there's a standard deviation. But is that the standard deviation for the population, for everyone, or is that the sample standard deviation? Well, that's the standard deviation from these 100 commuters. That's a sample standard deviation. So this will be a T value, not a Z. Oops, sorry, here we go. So this will be a T value, not a Z. So again, I did mention we can use the T chart even if it is Z. Like we noticed, this nice little extension at the end, this helped us a lot with confidence intervals and can definitely help us here. But this one is T. Well, if it's T, I need the area in the middle. And again, this is not trivial, everybody. 0.01 on this side. I can't tell you how many people jump to 99%. 1% and 99%, but you're missing that this setup always sets this up as 2 tails. So 0.01 here, leads to 0.01 here, a total of 0.02, which leads me to 98%. 0.98, 98% in the middle. So this is my confidence level or my central area. My degrees of freedom, well, I surveyed 100 people, so N is 100. Degrees of freedom is 99. Well, 120 is the closest I'm going to get for that. So 98% with 120 gives me 2.36 for my T-score. And again, it's up to me to realize I'm on the left. So that'll be a negative 2.36. Again, I have no problem if you just label it T. Some people like T sub C. That's the critical T-score, the T-score that separates the shaded from the non-shaded. But now I know I'm going to use this formula, right? If I use T here, I'm using T here. And if I already put a subscript here, this will be T sub T, the test T value. But now I use the rest of my sample data. I need my sample mean minus my population mean. Well, the sample mean, that's where I'm finally using the 41.8. I didn't use it to figure out it's a less than. I didn't use it over here. I'm finally using it in this formula, 41.8 minus the population mean. Well, even though we're challenging this value, we're going to use this as the population mean divided by the standard deviation over the square root of n. So the standard deviation over the square root of n. Now I just looked, I knew what formula I was using. I looked and found the values. That's my n, that's my x bar, that's my s, that's my alpha. I certainly do want to point out, plenty of people, after they read through the problem, before they start getting into their steps, they take a moment to find those values, to get your n, your x bar, to already think about, is this standard deviation s or sigma? So we can go in some slightly different orders here and there, but still have to stay on the same track for the most part. But now I'm finally doing computation. So my calculator, this is a little tough division here, so either use some extra parentheses or just be a little careful. I mean, the square root of 100 is a clean 10, but just use parentheses. 41.8 minus 43, close parentheses, divided by, new set of parentheses, 3.7 divided by. You could do the square root of 100. I'm just going to already realize that's 10, just to simplify a little. Close my parenthesis, negative 3.24. Again, be careful. These are still T's, Z's. If we start getting scores, bigger than 5, less than negative 5, those are pretty extremes. We've always kind of talked about Z scores, T scores, 3 to the left, 3 to the right. That covers a lot. This is a pretty extreme value right here. So, that's step 3. Now I make my final conclusion. I want to go back for one quick second, everybody, before I make that final conclusion. I just want to take 1 second and point something out. It's so easy for people to look at sample data and say, well, look, it took less time. If it used to be an average of 43, now the average is 41.8. Isn't that enough? Why do I have to bother doing all this other work? Isn't that clear that the subway is working, that average commute times are down? Well, not exactly, everybody. What if we didn't survey enough people? The more we survey, the more reliable these numbers are, but how far do we have to go? That's part of the reason we have to do this computation. Well, even if we survey a lot of people, if the standard deviation is really big, that kind of minimizes the impact. So again, it's not just so simple to say, oh, that's clearly less than that, so therefore we know that the alternative hypothesis is correct. That's the full process. That's why we need all the steps. So it's not only just that this is less than, that is conclusively less than. All this work covers that we did have enough people in our sample, that we didn't just get lucky and survey the right people, that this is conclusive. And that's where we are, everybody. I'm comparing the test T-score to the critical Z. And I want to know, is this in the shaded region? And it is. It's just an x-axis. So with negatives, a bigger negative than this one would push me further out here. That's in the critical region. Now, some people like to make that note. This is not a final conclusion, but for a lot of people, this is a good note they like to make. So they will just say something like, since the test value is in the critical region, we will reject the null and accept the alternative. That's the situation we are in. But that is not an acceptable final answer, everybody. That is a generic statement of what we will always be looking to do, but we have to put it back into the context of the problem. And that also goes back to the alternative hypothesis. I'm not saying the new average commute time is 41.8. All I have done is conclude this is no longer true, this is. So I would now say, and again, even answering the question, is this proof the new subway line reduces commute time? Well, yes. From this information, this is true and this is no longer true. So this supports this statement. Yes, there is evidence, proof, however you want to phrase it, enough evidence to conclude the new subway reduces commute times. Oops, sorry. Yes, there is evidence to conclude the new subway reduces commute times. I think that certainly answers the question the way it was asked. Other people, they try and get a little more specific to the numbers. There is enough evidence to show the average commute time is now less than 43 minutes. They really, again, go right to the alternative hypothesis. So there's a little variations here, but that is a good, satisfactory answer. And again, just writing this without enough work here, on this last test, on your final for these types of problems, I always point out that these answers need support, and this is the support, so that you're making the right conclusion and that there is valid work behind it. Now, maybe we goofed our computation, but we still get the right conclusion. Again, I'll always give you partial credit. If you goof the arithmetic and get negative 1.24, well, that would be over here. You're not in the critical region, but I would just ding you a point for having the wrong t-value. But if you make the right conclusion, that would just be 1 point off. So if you had negative 1.24, we would not be in the critical region. We would fail to reject the null, and we would say something along the lines, we wouldn't say the new subway line has failed, but we would just say simply there's not enough evidence to show the new subway line works. So again, we're not accepting failure, we're just pointing out there's not enough information. Okay, so that's a long problem. Let's do two more. Let's change our situations a little bit. This next one, we're looking at a shopkeeper, a store owner. He decides to invest in some local advertising, hoping to increase his store's sales. After he does his advertising, he looks at his next 36 customers, and they spend an average of $27.30. Before advertising, the average spending from all customers was $26.15, with a standard deviation of $5.78. Using alpha is 0.05, is there enough evidence to show the advertising worked? So a completely different situation, but it still has all those elements of a hypothesis test. Someone's trying something new. He's using advertising, but he's doing it hoping to increase the amount of spending, to increase the amount of money that his store makes. That's a perfect hypothesis testing situation. Then we get some information, getting to the end, using alpha. Well, previously I said level of significance. Now I'm just handing you alpha. But either way, that's another huge indicator that it's a hypothesis test. But even reading the final question here, is there evidence? Is there proof to show the advertising worked? Is there evidence to show the store has increased its sales? So a lot of little ways I could have phrased that, but all that would lead to hypothesis testing. The other little thing if you're just jumping and trying to label information, and if you look at the previous problem compared to this one, you'll notice the order I gave you information changed. I start off with the situation, but in this one, I immediately start talking about sample. And then down here, you'll notice this information is talking about all customers. So we can't just always assume our null hypothesis is given, then there's my sample information and the alternative. We always have to read, clearly read, to see how the problems, the little differences from one to the next, but it's always all there. There's always information about what we used to believe to be true and how we are challenging that new information. So in this one, well, right off the bat, he's hoping to increase the store's sales. So in the previous one, I started talking already about the previous belief and then started talking about how we're changing. Here, I'm just jumping in. How are we trying to change? We're trying to increase store sales. So I'm kind of already giving you the alternative hypothesis first. So the null is going to have to be what the average is. The alternative, well, I want to increase the store sales. I want the average to be bigger than what it used to be. But now, what was it? And again, this is so easy to say, oh, that's the original mu, and then we're comparing, but then this is less than this value. So again, we got to be careful. What is it that we used to believe to be true? What is it that we know about everyone? Well, here, this is the before the advertising. That helps. But really, it's the word all. Sometimes we might get lucky and a problem will tell us the population mean or the population average or the population standard deviation. But here I try to be just a little sneaky, but the word all should be enough. This is the old idea. That is the old mean. And again, a good idea to include units. I'm not going to write out the full sentence, but we would say the average sale was $26, or the average amount spent by a customer is $26.15. And the alternative, well, we want to increase our sales. It says it here. Here, is there enough evidence to show advertising worked? Well, how does advertising work? If we sell more, so I clearly say increase here. Here, just the general inference from advertising working is that sales have increased. So greater than the 26.15. And we can again write the sentence, after advertising, the average sales are more than the 26.15. That our customers have increased their spending. So there's my null and my alternative. One quick thing before I move on, everybody. Notice, I'm not writing HO equals 26.15. I'm using the mu. It's not the null hypothesis is 26.15. It's the null hypothesis is the average amount spent equals $26.15. So just be careful with that, everybody. We need the mu symbol here. But now it's a greater than. So now my critical region will be the right-hand tail. Greater than goes with right hand. Alpha is given. One tail, that alpha entirely goes on that side. Is this a z or a t value? Well, that depends on the standard deviation. Well, there's the standard deviation. Is that population or sample? I said it before, but that went along with the all. That's population. So this will be a z this time. So again, everybody, this is where you can use the z-score chart to get that z. But you'd be finding the closest area to 0.05. Okay? And where would that be? That would be right between these two. But this one, it's exactly split. These are both equally distance apart. I would never give you a hard time if you used either one of these. Just notice this chart is giving me negatives. We'd have to realize we're on the right side, so this would be a positive. And we would get either, sorry, where was I? This one or this one. So 1.64 or 1.65. But if you use the T chart, we still have to think about this picture. Remember, it's still either one of these charts. You still have to do a little bit of reasoning. Here, we knew it was Z, so we're trying to find the closest to the area in the middle to pull back to get the Z. In this one, it's about getting your picture to look like this. So if I know 0.05 here, I'd have to also put a 0.05 here, would give me 0.90 inside of here. So 0.90, 90% or 0.90, and there's my Z. Notice before with the other chart, I said either 1.64 or 1.65. Notice this one exactly split the difference. It found the average of the two. So again, that's what we should have done even with the Z chart. There's plenty others that we would get a closest one value, but since it was a perfect even split, that's why either one would work there, or best the average, which is what this is giving me. So Z is 1.645. I will get my test Z score. So sample mean minus population mean divided by standard deviation, population standard deviation over the square root of n. Okay, X bar, there's the 2730. That's the average amount spent in my sample out of these 36 customers, minus the population, the 2615, over my standard deviation, over the square root of n. And one more time, n happened to be a clean, perfect square. Doesn't always happen. It's a nice thing, but doesn't always happen. So this one, I'll put the square root in my computation this time. But similar to the previous, you could do 2 steps, everybody. This one's not bad. Here you'll probably get some ugly decimals, so just don't round, right? Try and get a lot of decimals, and then do the rounding on your next part, on your answer, or all at once. But if you do it all at once, good use of parentheses. 2730 minus the 2615 divided by the quantity, the quantity of 5.78 divided by the square root of 36, close the square root parenthesis, close the parenthesis for the denominator, and I get a 1.19 z-score. We compare. And this is exactly what I was saying on the previous page, everybody. It's easy just to look and say, look, these people are spending more money than they used to, so the advertising worked. But it's only 36 customers. And we had a pretty big standard deviation. So again, maybe I just got lucky with these 36 customers. Maybe my next 36 customers will only spend $25 on average. So that's the idea behind all this. But now, how do we conclude? Well, step 1, we got our hypotheses. Step 2, critical region, critical value. Now I'm comparing. Does this put me in the shaded region? Well, this value, now I'm on the positive side. I need a bigger positive to be over here. So like 1.7, 2, 3, anything like that would be bigger, but this is smaller than that. So I'd be over here. And I don't need to know, am I over here? Am I over here? It's just about, am I in the critical region or am I not? That's all it is, everybody. And sometimes you might say, to be quite honest, if you were doing this for your job, you would often play games with alpha. You would say, well, it doesn't work for alpha's 0.01, doesn't work for alpha's 0.05. And you could keep playing these games. That's some parts where some people can try and mislead, but there's a lot of ways for people to know how far your researchers had to go to make their conclusions work. But again, that's going above and beyond. All we need to finish is this in the shaded region, and this time the answer is no. It's not because this one is a Z and the previous is a T. That's irrelevant. It's just about comparing these values. I'm not in the critical region. Just like the previous, I could write that out. Test value not in the critical region, failure to reject the null. That's fine, but that doesn't finish the problem. Get that in context here. So all I would have to say here, is there enough evidence to show the advertising worked? No, there is not. I'm not saying the advertising failed. I'm just saying there is not enough evidence to conclude the advertising I could just say the advertising worked, but I'll be a little more specific. There's not enough evidence to conclude that the advertising increased sales. It may work. He should continue to test and see, but at this stage, we don't have the evidence to prove that the advertising has had a successful impact. Okay. One more, everybody. You see, long problems, but again, a very methodical approach to going through each one of these. So now one more, everybody. A journal published results from a survey regarding how many times per month do people eat out at restaurants. So again, just a whole bunch of different examples. My first one, I tried to talk just a little bit about, the ideas of just city planning, some sort of logistical information. I could have done a medical problem in a similar sense. The second problem, looking at a little bit of a business situation. And now just trying to take one more, just again, a lot of different possibilities for how hypothesis testing can work. So this is more of just some, popular information. How often do people eat out? You could say some businesses would clearly like to know this so that they could plan accordingly, but maybe this is just some fun information for people to know. But we've got results. They're looking how many times do people eat out at restaurants. And they found the average was people eat out 8.2 times per month. A local food critic thinks this number is not accurate. So he surveys some people, finds their data is normally distributed. That's just a little bit of, the T&Z, just covering all the bases. T&Z will continue to just use the idea, what is the standard deviation that we know? So that's just there, but he surveys people and they eat out a mean of 9.1 times each month with a standard deviation of 1.7 times. Is the food critic correct? The journal's number is incorrect. That's a little funny to say correct and incorrect. That sounds a little awkward, but we're basically testing the food critic's claim. So notice, I'm not going to the journal. We're talking about the food critic. Is the food critic correct? He's the one making the claim that we are challenging. Okay. Oh, just one little thing. I didn't want this to be a perfect square. Let's only survey 20 people this time. So one more time. Food critic correct. Test using alpha, well, that's a clear indicator this is a hypothesis test. But even without that, just the overall idea, testing the critic, is all about the idea of hypothesis testing. So, null hypothesis, what are we testing? Well, the food critic is challenging what the journal published. So the journal says people eat out an average of 8.2 times. Mu equals 8.2. And again, one more time, I'm perfectly fine if that's all you write, but to understand what this says. The average amount of times people eat out a month is 8.2. The alternative. If you jump down to the sample data, you think that people eat out more than 8.2. Mu is greater than. But that's not what he says. He doesn't say he thinks people eat out more than that. He just says he thinks this number is not accurate. Maybe he didn't know. Maybe he's just guessing. He didn't know if it's more or less. He just didn't think that number was accurate. That is how we'd end up with a not equals. Okay? So one more time. I'm not looking ahead at the test data from my sample. I'm doing it based off of what they actually say. This number is not accurate. All that says is not accurate. It doesn't say, or that the number is false, the number is not true, the number is wrong. Any of those statements don't indicate it clear. It should be bigger, it should be smaller. And there's nothing after that comes up to say that either. That's what leads me to the not equals. Now I've got a two-tailed test. So now my alpha has to be split up. Now, it's not 0.01 in each, it's the total shaded region is 0.01. So cut that in half, you get 0.005 in each tail. So that would be a total of 1%. So that would leave 99% in the middle. Notice that's very different. The previous two, when we only had one side, I had to pretend 0.05 was also here to give me 90% in the middle. But in this one, that alpha was already split up. So by dividing that in two, the total shaded area gets me right back to alpha. So that gives me 0.99, 99% in the middle. Should I get a T or Z? Well, I'm going to get two values here because I'm getting two shaded regions. But should they be T or Z? Well, it's got to be about the standard deviation. There's the standard deviation. This standard deviation goes for the 20 people that he surveyed. So that is the sample standard deviation. We are going to get T values. So now back to my T chart. 99% in the middle. So I'm using this one with 20 people. So 19 degrees of freedom. I'm getting 2.86. But now I'd have to interpret. So that's a positive 2.86 on the right and a negative 2.86 on the left. Now when I get my test T, again, it can't be in both of these. It's just, is it in any shaded region? So I'm kind of comparing to both of these. But ultimately, and this is partially why I don't like the p-value idea, everyone, that I mentioned. I think this is a very good problem that throws people off in a lot of ways. But if you do the test value, the test T will be my sample mean minus my population mean divided by my standard deviation divided by the square root of n. And again, I like the subscripts. You don't have to use them. It's perfectly fine to have T here and T here, but just know how to compare them at the end. I just like that tiny little bit. Critical T coming from this and the chart. Test T coming from the actual data. So now when I do this arithmetic, and again, I intentionally made this one a little tougher, so you kind of have to do this all at once. 9.1 minus 8.2. Quantity 1.7 divided by the square root of 20. I get 2.37. And one more time comparing. We've only done 3 problems, everybody. I don't want you to think, well, it's more common for you to reject the null than it is for you to have a failure. Anything is possible, everybody. This is just 3 problems. And in the first one, we did reject the null. The second one was a failure. And this third one is also a failure. 2.37. It's a big T value, but not big enough. Not for this one. And this is what I was just mentioning a moment ago. That's still a big T value. So if someone was actually doing this and they wanted the food critic to be correct, they'd almost certainly follow this up by trying alpha's 0.05. But that's not your responsibility, everybody. You were given this alpha. Well, with this alpha, this is not in the critical region. So not in the critical region, failure to reject the null. And in that sense, one more time, we're not going to say the food critic is wrong. We're just going to say there is not enough evidence to support the food critic and his claim. So again, some fairly lengthy problems. These one, very methodical, but a lot of steps. Have to read carefully, and then get the practice to move through one step to the next. The last thing I just want to do is just again come back and point out all this. If you read 10.3 over, which you'll see, there's no homework from that. 10.1 just gives you a little bit of homework practicing setting up your hypotheses, the null and the alternative. And then 10.4 is the rest of the homework and your hypothesis testing for mean, for averages. But if this was a proportion, just like we did with the idea of confidence intervals of proportions, we could do similar things. If I already know some information about the percentage of people who commute to work, or the percentage of people who support a particular politician, and well, is there new information that changes that proportion? maybe the proportion of people who supported Donald Trump was this, but now after his coronavirus response, we think that proportion is less than what it used to be. Well, we go collect some sample information. The one nice thing of proportions, just like we mentioned for confidence intervals, you never use t. It's always z, but you'd still be talking about, is your claim a less than, greater than, or not equal compared to the original? You'd still get one of these three different tail situations. You'd do the same thing. It would always be z to get your critical z. We'd have a similar formula to use our test data to compare, and then we'd make same conclusions based off the same ideas.